Yeah, it's laundry day. So I went to the laundromat, and somebody there asked me an interesting question. This is what they asked me. They said, we got this wonderful machine that makes our clothes dry, but it also works sometimes clothes dry by themselves. So what makes our laundry get dry exactly? What makes our laundry get dry? Well, here's the answer. We've got a hydrogen atom here, and another hydrogen atom here, and of course an oxygen atom, which is somewhat larger up here. And this gives us our familiar water molecule, H2O. And just to keep things simple, for this video, water is going to be a blue circle. So I'll circle this whole structure. And anytime you see a blue circle like this, we're really talking about H2O. A couple things to keep in mind, or one thing to keep in mind really. H2O, because of these two hydrogen atoms that tend to migrate towards one end of the molecule away from the oxygen, we're going to have a very weak positive charge on one end of our molecule, and by contrast on the other end we're going to have a weak negative charge. This is all you need to know to remember that water forms these very short-lasting, temporary, and not very strong hydrogen bonds, in which case a water molecule may cling to another water molecule, or it might cling to something else because of this polarity. So this brings me to the issue of when something is wet, or when there's water, that just means we've got a lot of water molecules close together, and they're constantly forming and unforming and reforming these hydrogen bonds. And so some of these bonds will only last for, a few milliseconds, but there are so many water molecules constantly coming in contact with each other in the water that there's always a majority of them connected, and so you've got this amorphous kind of blob of water that tends to stick to itself, even though it's very almost infinitely flexible. But let's say we add some energy to this water. This could be in the form of heat from a cooking stove or a fire. This could be sunlight or other radiation. The light gets absorbed and turns into heat, but basically energy is added to these molecules. They become excited, and as they become excited, they move around more rapidly, and therefore the hydrogen bonds break more readily. And so in the end, some of these molecules are going to break free. And as they do, they go off into the air and they start moving at random, and they are much less likely to come in contact with one another. And so now this liquid state is passed on to a gas state, or we say it is now vapor. And of course, you can also remember if the opposite happens, if the water gets too cold, it will form these very rigid structures, crystalline structures. We call it ice when we're referring to water. And this is a solid state. But we're going to be concerned with the transition from liquid to gas today. So liquid, and that's gas. So suppose we have a puddle of water. We have a bunch of water molecules floating around. One thing you should note is that you do not always need to have energy input to cause this evaporation to take place. These molecules are constantly turning into vapor, and from vapor into liquid, and from liquid to vapor by random. And so from time to time, just for no particular reason, a water molecule will escape from this mass of water, the puddle, and it will just become a molecule of vapor. It'll return to its gaseous state. And here goes another one. Likewise, we've got water vapor floating around out in the atmosphere. From time to time, two or more water molecules in vapor form will collide, stick together, form a hydrogen bond. When enough of these happen, we get condensation. The water turns back into a liquid. So you've got this exchange going on, but now it's not always going to be an even, steady state where they exchange at the same rates. Let's say we've got a small dish or a saucer. Let me just draw a picture here. Not sure what that is. It's some kind of container holding water molecules. So it's holding water. We'll show that the water is in this molecular form, all these little tiny molecules filling this container. This will happen with any body of water, whether it's a cup or a puddle or a swimming pool. But the shallower it is, the more quickly this will take place usually. So from time to time, just at random, as we said, a water molecule will escape and become gas. However, when this molecule combines with others and returns to its liquid state, or if it just gets cool enough it returns to the liquid on its own, it's not necessarily going to happen right over the plate. This molecule could float off over here somewhere. or it might fly away this way. Here goes another one. This is another molecule. It leaves and it flies over here. So even if it turns into liquid later on, it's going to be liquid that gets inhaled into someone's lungs or comes down in part of a raindrop. And so over time, we're having a net loss of our water molecules. So when one of these goes, we have to erase this one that's in here because it's not going to return. Likewise, this one. Eventually, you lose all of your water molecules from this container, and that means it has effectively dried out. At this point, you probably understand what's going on with your laundry, but let's just illustrate it. We've got our green shirt here. It's in the laundry, let's say. It got washed. And now if this green shirt's just out on the line, drying, you know what's going to happen. The wind blows on it, or even if it's just resting in the air, these molecules leave of their own volition from time to time. And assuming they go somewhere where they're not in contact with the shirt, then even if they condense and become water again, it won't happen inside the shirt. So over time, there's a net loss of liquid until this shirt is dry. Given that, you probably understand what's going on in a dryer. There are actually two things that are happening. One is that this shirt is moving around. It's spinning and being thrown, and it flops around. This exposes it to much more air and causes the water molecules to leave it all that more quickly. So even just tumble drying it without any heat would already help the shirt dry out faster. But then, of course, dryers usually add another element to this, and that is they provide a lot of heat. And as this heat goes into the shirt, we're adding energy to the system, and so you know, of course, what happens. This causes even more water molecules to leave more quickly as they become agitated. And in a much shorter time, our clothes are completely dry.